solving equations that are quadratic in form. In order to do this, solving equations that are quadratic in form, we're going to use a method called U substitution. Technically, these equations are not quadratic equations. They're just quadratic in form. So what this method does is it converts these non-quadratic equations into quadratic equations, allowing us to use whichever method is appropriate to solve. The steps for doing that: make sure the equation is in standard form set equal to 0. Then what we're going to do is we're going to take the variable u and set it equal to the middle term's variable. Then we're going to find u squared, or basically square both sides of that equation, and substitute those two values, u and u squared, into the original equation, giving us now a quadratic equation to solve. So solve the quadratic equation. At this point you solve for u, so all you have to do is go back and substitute the original variable back into the equation and solve for it now. So example 1 is certainly not a quadratic equation, but it is quadratic in form. The first term, more specifically the variable in the first term, is the square of the variable in the middle term. Now it's already in standard form set equal to 0, so use substitution. We're going to begin by setting u equal to the middle term's variable, which is just the x squared. Then if we square both sides, that gives us u squared is equal to x squared squared, or x to the 4th, which is the leading term's variable, exactly what it should be. So we substitute these two values into the variable. X to the 4th we set equal to u squared, plus 8x squared, we set x squared equal to u. The constant 16, of course, doesn't change, equals 0. So now we actually do have a quadratic equation that we can solve. Use whichever method's appropriate, which will typically be factoring. Extracting the roots will not work, but this factors into u plus 4 times u plus 4, which gives us u is equal to negative 4 and u is equal to negative 4. So only one distinct solution for this quadratic equation, u is equal to 4, but we haven't solved the original equation yet. The original equation had the variable x. That's what we need to solve for. We're going to substitute x back in for u here. So we set u equal to x squared, so substitute x squared back in there for u, and solve this equation. Take the square root of both sides, not forgetting your plus or minus, so x is equal to plus or minus 2i. Now typically we'd have to do it to the second equation, the second solution, but in this case, since it's the same, obviously it would be redundant. So x is equal to plus or minus 2i, the solution to the original equation. Example 2 is right now a non-quadratic equation, but it is quadratic in form. The first variable is the square of the middle term's variable, and we see that when we set u equal to the middle term's variable, square root of x. Already, of course, making sure it's in standard form set equal to 0, and it is. So now when we square both sides, u squared is equal to just x, the variable in the first term. So substitute these values into the equation. U squared plus 13u minus 30 is equal to 0. Solve this quadratic equation. U plus 15, u minus 2 is what it factors into, which gives us two values for u. U is equal to negative 15, u is equal to 2. So now we just have to take it a step further and solve for x again. Since these two solutions are different, we have to substitute x back in for each one, so that gives us the square root of x is equal to negative 15, and the square root of x is equal to 2. Solve each equation, square both sides. X is equal to 225, x is equal to 4. However, like all equations, we always want to check our solutions, or should anyway. But technically this was a radical equation, and if you recall when we covered radical equations, you have to check your work, because sometimes the solution just doesn't work. And 225 does not work, which made sense if we looked at it back up in this step. That equation told us that the square root of x was equal to negative 15, and we know that cannot be equal to a real number. So only one solution, x equals 4. Example 3. A non-quadratic equation, but is quadratic in form. It's in standard form set equal to 0 already, so let u equal to the middle term's variable, x to the 1/3, which makes u squared equal to x to the 2/3. Substitute these values into the equation. U squared minus 4u minus 45 is equal to 0. Factors into u minus 9 times u plus 5 is equal to 0, which gives us two values for u. U is equal to 9, and u is equal to -5. Continue solving now for x. Substitute that x to the 1/3 back in for u in both of these equations. And now solve for x. Well, to get rid of an exponent of 1/3, we can cube both sides. And if you don't recall that or don't notice that, remember a fractional exponent is nothing more than a radical, so that's the same thing as the cube root of x, which we know how to get rid of a cube root. Cube both sides. So x is equal to 729, the first solution. The second one, cube both sides. X is equal to -125. And in this case, both solutions do work. You have to have them both. And example 4. Example 4 is already a quadratic equation. Now, it's certainly not in standard form, so we could get it in the standard form relatively easily. FOIL the x plus 7 squared, distribute the two combined like terms. But this is an example from the homework in that technically it's quadratic in form as well. If we let u equal to x plus 7, u squared then, of course, would be x plus 7 squared, which is the first term. So if we substitute these values into the equation, we can solve it right away by factoring. It factors into u plus 6 times u minus 4, giving us two values for u. U is equal to -6, u is equal to 4. Now we just go back and solve for x. We set u equal to x plus 7, so substitute it back in to both of these equations, giving us x is equal to -13 and x is equal to -3.